So plan today is to talk about the rest of chapter 6. So 6.1 was talking about the maximum likelihood estimate. 6.2 talks about another method of estimation called the method of moments. And then we can kind of talk about some characteristics of estimators in general if we have some time at the end, like what makes an estimator good versus a bad estimator. And so just so you guys know, for the homework that is up and due, nothing is due today. For the assignment that is due next week, you should be done after today's class. You'll be able to take a look at question 3, and I would definitely encourage you to be done with the first 3 questions on that assignment by Wednesday, so that we can just focus on doing confidence intervals on Wednesday. Okay, any questions before we get started for today? So we have a smaller crowd here, so feel free to use the time as best to your advantage. So if you want to stop me, please don't hesitate to just ask for some clarifications. So the idea behind the method of moments is it's almost like it's a model. We're going to fit a model to our sample data like we did with maximum likelihood estimator. With the method of moments, we're not going to try and come up with a likelihood function and then say, based on our sample, what's the most likely value for the undetermined parameters. Instead, we look at our sample and we think about what is the mean of our sample. And then we think, okay, well, the distribution, the underlying population distribution, that should have the same mean. And then we think, okay, our sample has a certain variance. We would want our population distribution to have a variance which is the same as our sample. So it's more of like a curve or property fitting thing. It's almost like, here's some data. We want to find a model for the curve through those points. Let's make sure it has the right first derivative, the right second derivative, the right third derivative, and so on. So depending on how many parameters your model has, you're going to have to set up the same number of equations. So for us, we typically have 1 or 2 undetermined parameters in our model. So we'll have to set up either 1 or 2 systems of equations to solve. Okay, so that's kind of the first kind of goal here is we want our population to have the same properties as those that we observed in the sample. So kind of next is, how do we measure those properties? And so we're going to use what are called the theoretical moments. So the kth theoretical moment, as you guys looked in for the reading quiz, right, that is just the expected value of x to the k. So for the first moment, it's just the expected value of x. So that tells us the mean. So this tells us the center. So basically, we want the center of our population to be the same as the center of our sample. The variance is the expected value of x, excuse me, I should say the second moment is the expected value of x squared. And that's related, not equal to, but it's related to the variance, right? Since we know that the variance of x is equal to e to the x squared minus e to the x squared. Proved that earlier in the semester. So basically, once I know the first moment and the second moment, we can find the variance. And the same goes for higher moments. So the third moment is related to the skewness. So that's what I've drawn over here. And so here are some different shapes. And I realized that I think I stated something wrong earlier when someone asked about skewness and how we describe skewness. I'm just basing that on the fact that I saw a number of similar mistakes on homework. And so I imagine I might have been the source of those mistakes. So I apologize. Let me just clarify them. So when we have a distribution that looks like this, we have a tail over here. And most of the values are on the left. And we describe this skewness in the direction of the tail. So we would say that this distribution either has positive skewness, or we would say that it's skewed to the right. This has 0 skewness, the second one, and that means it's symmetric. And this last one over here, the tail is going to the left. So this is negative skewness is one way to describe it, or we can say this is skewed left. So when we describe the skewness, we do it where the tail is. So the third moment tells us something about how the data might be skewed or symmetric, or which direction it might be skewed. The fourth moment, in case you're curious, is called the kurtosis. And the kurtosis, whoops, sorry. The kurtosis measures how peaky the data set is, in the sense that this data set has a really sharp peak. It's all very much concentrated at the peak in the middle. So it has a large value for kurtosis. This distribution over here is a bit flatter, say, than a normal distribution. So this would have a small kurtosis. And this normal distribution is kind of like the baseline for kurtosis. So a normal distribution has a kurtosis of -3, or equal to 3, excuse me. So in any sense, the goal here is we're going to make sure that our population has the same mean, has the same spread, has the same skewness, has the same peakiness as our sample. And as far as we're concerned, we're really going to be at most dealing with models that have 2 parameters. So we're going to really just need to think about the first 2 moments. But these are things that have these things being the moments. Lots of applications throughout probability and statistics. So you may have seen them. I'm sure if you've taken probability, you have seen them. Any questions? Okay, so the way that we calculate the theoretical moments, if we knew what the population was, then we would know what the PDF is the same way that we calculated them before. So if it's a continuous random variable, we integrate. If it's a discrete random variable, then we sum over all values of x. The problem for us is going to be we don't, so we're going to have some parameters in our PDFs that are undetermined. So we'll have kind of, we think that the PDF should have this general form, but again, the problem is still the same as it was last time. How do we figure out what the values of those parameters are? So we're going to compare these theoretical moments to what are called the sample moments. And that's what you guys checked out for the reading quiz for today. So for example, if we take the following distribution, if our PDF had 2 parameters in here, one is lambda and one is delta, then if we wanted to find the first and second theoretical moments, we have these 2 integrals to set up and solve. So for the first theoretical moment, right, I'm just going to take and plug this in for x, for f of x, excuse me. And then we would integrate over our domain, which in this case is not negative infinity to positive infinity, but we know that x is bigger than this parameter delta. So we would integrate from delta up to infinity. And let me just skip the calculus there, since I don't want to spend our time doing a whole bunch of integrals, but rather seeing how could we make sense of those integrals. But over here, we would just integrate this with respect to x. And then we evaluate it at delta and go all the way up to what happens as the upper limit approaches infinity. Any questions? So I would definitely leave that as you know, an exercise for you to think about integrating that. But delta and lambda, these are constants. We're just treating them like constants whose values are undetermined at this point, and x is our variable. And for the second moment, same idea. We're going to integrate over the domain, which is from delta up to infinity. But now we have an x squared here. And so that is a little bit more difficult to integrate, but not too bad. Oops. It looks like this. Okay, and hopefully all of those things are lambdas. There are no more x's over here. So if my x's are looking like lambdas, this is a lambda, this is a lambda, that's a lambda. After we've integrated and evaluated the integral, there should be no more x's. So these theoretical moments, just to come back over here, these are going to depend on however many parameters we have. In our case, it was delta and lambda. When we calculate the moments, these are going to be values we calculate. So if we're told, in addition to this is what the PDF of the population is, and now we're told, okay, we pick a sample from that population, and our sample, the first value was 3, and then 4, and then 5, and then 8. What are the likely values for these parameters, delta and lambda? Let's find some estimators for them. So the moments we would calculate by first moment would be the average of them, the mean. Second moment would be the average of x's, the x squared. So this calculation gives us 5, and then for the second sample moment, we get 28.5. So these are our numbers. Okay. Any questions? This is my first class speaking out to an entirely blackened out screen, so I hope I'm doing okay. Okay. Yeah, so I don't see you, but if you've got questions, I hope you're open to ask them. Okay, so when we're doing this method of moment estimators, kind of like you could do step 1 and step 2 in any order. Maybe step 1, if you want an easier first step, it would be, okay. Look at how many parameters are in your model. Okay, we have 2, lambda and delta. Then we're going to calculate as many sample moments as variables, or excuse me, as parameters. And that's what we did in question 2. And then we're also going to calculate the same number of theoretical moments. That was, I think, question 1 that we did. Yeah. Then we're going to set the sample and theoretical moments equal to each other. And solve the corresponding equations. Which means we're going to try and figure out what values are the parameters. So we've got 2 parameters, and so that's why in questions 1 and 2 we found the first and second sample and theoretical moments. So that means we're going to take this information over here. So that was our theoretical moments. And let me get my sample moments. And then we set them equal to each other. So I would set delta plus 1 over lambda equal to 5. And then I'm going to take the delta plus 1 over lambda squared plus 1 over lambda squared, and I set that equal to 28.5. This is the second moment. And what we get is a system of equations, okay? So I need to simultaneously solve this. So these questions involve quite a bit, involve some calculus. We're gonna need to do some integration. We didn't work through those steps, but that's something you wanna be careful about doing those integrals. And then it also is gonna involve some algebra for solving systems of equations, and these systems are not going to necessarily be linear. So we're gonna have to be a little creative with how we solve these. So I've got a system here, and again, I'm trying to solve this simultaneously. So I want to find values for delta and lambda that at the same time would solve both of those equations. Okay, we got a small class here today, so that means you should feel free chiming in some thoughts here. Does anyone have any suggestion about how we could solve this system?
Two equations, 2 unknowns.
That was great. We had 2 people chime in right at the same time. So sorry, I think Stephanie and Jonathan both, you guys were both saying something. Since the this rectangle is on you, Stephanie, do you want to say what you had shared before?
Yeah, I was just gonna say we could put 5 into the delta plus 1 over lambda.
Yeah.
In the second equation.
That's a good plan. Jonathan, what were you suggesting? I think it was Jonathan.
Same thing. It was just 2 equations, 2 unknowns.
Yeah. Yeah. So I think what is going to be useful in a lot of these problems is using some sort of substitution strategy. Elimination strategy, right? That's useful when you have linear systems. That might not work here. So yeah, from the first equation, I know that delta plus 1 over lambda is 5. So let me plug that into the second equation. So that would give me 5 squared plus 1 over lambda squared is 28.5. And that's great. Right now we just have one equation with one undetermined parameter. We can solve for lambda. We can do something like 1 over lambda squared is 28.5 minus 25. So lambda squared is 1 over 3.5. So therefore, solving for lambda, right, we would take the square root of that, and I'll just approximate that. And we would call this the method of moments estimator for delta, or excuse me, for lambda was the first one we did. Okay, so we got these equations up top from setting the moments, sample, theoretical equal to each other. We've got a system of two equations and two unknowns, and then we just, try and solve that system. And so once I've got my value for lambda, now I can come back to the top equation and say delta plus 1 over lambda is equal to 5. And then that will give us at the end, the hats mean estimator, and then the subscript MON just means this is it's indicating the method that we use to get that estimator. Okay, any questions? Okay, so if not, let's take a look at the next example, which deals with uniform distribution. So this is very, very similar to homework question 3 on your homework. You just have a different sample, but you're asked to do the method of moments for a uniform distribution. So we'll go through something here. Hopefully, this will help put you in the right direction for your homework. And again, hopefully you get through those first 3 questions by the time we meet again on Wednesday. Okay, so for question number 4, let me just copy it and come to a fresh page. That did not copy it. That'll get most of it. So let's see. It was, we had a 7 and a 10 and 1 and 3. Okay, so that is our data. Sorry, that part got chopped off. And so we're gonna do the same approach here. Just to have these steps in mind. Okay, so we're going to go ahead and take a look at how many parameters do we have in our model. And here we've got an alpha and a beta. So we have 2. Okay, next we'll do sample moments. So M1 would just be the average of our sample. So I'm just going to take 1 plus 3 plus 7 plus 10. And we have 4 things in our sample. So that gives me, where are we here? 5.25. And then M2, I would take the average of the squared values, which comes out to 39.75. So those are usually, hopefully that step is pretty straightforward, just doing some calculations. Okay, then step 3 is to find these theoretical moments. And so for this, we could either use the PDF for a uniform distribution, but here would be good opportunity to just recall some facts that we learned about uniform distributions. And one of them was the average value, right, is the midpoint between the maximum and the minimum value. And the other one that you may not recall is the variance. We also have a formula for that. Which is the distance between the max and the min squared, and then we divide that by 12. But we don't want the variance, right? We want the second moment. Right, so we want to find out what that green thing is. That's the second moment. It's related to the variance, but we don't want the variance itself. We're going to take the second theoretical moment, set it equal to the second sample moments. We just want the expected value of x squared. So here we can solve for e of x squared, right, by taking the variance and then subtracting, or excuse me, right, we can add e to the x squared to both sides in order to solve for the second theoretical moment. So I'm going to add that e to the x squared, and we know that e to the x is this. Oops. So here's our first sample moment, or excuse me, theoretical moment, and here's the second theoretical moment. We could have found these by finding the PDF and then integrating x times the PDF, integrating x squared times the PDF. That would work just fine too. Any questions so far? Okay, and so then our equations are going to be, we want sample moment 1 so we have first theoretical moment, alpha plus beta over 2 should equal the first theoretical, the first sample moment, which was 5.25. Then we have the second moment, And that should equal the second sample moment, which was 39.75. So that's our resulting system of equations. So the sample moments, where's calculation, I think the trickiest part in this process is finding the theoretical moments, because that either involves some calculus or some knowledge of some of the common distributions that we've talked about earlier in the semester. And then the last step is the algebra. Any questions about where we got these two equations from? Okay, well then I will give you guys some time to try and work your way through that. So go ahead and try and solve that. I'll just sit here quietly, but if you have some questions as you're trying to solve it, you are welcome to chat me or talk them in. Otherwise, I will give you guys a moment to gather your thoughts and try that on your own. Okay, well, thank you for getting those suggestions in. Yes, so we can take a similar approach to the previous one, right? And that is, we know that alpha plus beta over 2 is 5.25. So we can just plug that in to the resulting equation. And then I can, bring the 5.25 squared over, take the square root, bring the 12 over, and in any case, we can solve this equation and get that beta minus alpha is 12.093. Again, that's just taking the equation that I have up here, solving it for beta minus alpha, right? So bring this over, multiply by 12, and then take the square root. Okay, then we have a second equation, right, which is this one. So when I did this substitution, the difference here is we still have two parameters left, right? In the previous case, that did the trick, and then we just had one equation with one unknown that we could solve for. So this simplified it a little bit, but we still have two unknowns, so we can compare this, say, to what we know from if alpha plus beta over 2 is 5.25, that's the same thing as saying beta plus alpha is 2 times 5.25. And now we do have a nice linear system, actually, so we can just add these two equations together and get 2 beta is 22.593, and then dividing that by 2 is 11.297. Then I can plug that estimate into the second equation for beta, and I've got alpha plus 11.297 is equal to 10.5. And then solving that for alpha, we get a negative value here. For the parameter alpha. And so just to kind of compare these estimates to the sample that we had, we have a uniform distribution. So we pick these values from a uniform distribution. So it makes sense that, beta, that's representing the upper endpoint of my interval where these things are uniformly distributed. So what we see is that the estimate for the upper limit is a little bit bigger than our maximum value. And the estimate for the smallest value for which the distribution is defined is a little bit smaller than our minimum value. So it makes sense that we're getting these values seem to have come from a uniform distribution from a little bit smaller than 0 up to a little bit bigger than 11. So it's good when we get these estimators to stop and think, okay, are these reasonable? And I think these would be pretty reasonable estimates for the uniform distribution from which these values were picked from. Any questions? Okay, so hopefully, if not, then you should be good to go on that homework problem. Okay, so then I want to talk a little bit about a couple of properties of estimators that might be desirable. So one property of an estimator that we've talked about is whether the estimator is biased or not. So just recall that the bias of an estimator is equal to this. So we would say the expected value of the estimator minus the actual value of the parameter should be 0. So this would mean like we would expect our estimator to equal the parameter, which is good. So if this equals 0, then we say it's an unbiased estimator. And if it does not equal 0, then we say that it is a biased estimator. So here's a quite complicated thing that I don't want to get into all of the details here because this is worked out in great detail in the textbook. But when we were taking a look at a normal distribution, okay, and we pick a sample from that population, and we want to come up with estimates for these parameters, mu and sigma, say using the maximum likelihood estimate, what we talked about last time. I'll just say what you can see is that the maximum likelihood estimate for mu is going to equal the same calculation for x's. And the MLE estimate for sigma is kind of the same corresponding calculation, but with the sample. And if we want to see whether these are biased or not, is we want to see, okay, does this equal 0 or not? So in other words, we would take the expected value and so using properties of expected value, we can pull out the n, 1 over n. And then if I take the expected value of the sum of xi's, right? The expected value of each xi is mu sub x. And we have n of them since, right, we're summing up all n xi's. So that's how we could check that the maximum likelihood estimator for the mean is 0, and that's because the expected value of that estimator is equal to mu, equals the thing we're trying to estimate. It's a more complicated check, but we could do the same sort of thing for the estimator for the variance. So let's not think about standard deviations, but we'll think about, let's see, is the estimator for this variance unbiased? Well, then what I'd want to see right, does that difference equal 0? And this estimator that we defined, that's over here. So we'd want to calculate the expected value of sigma squared, our estimator for sigma squared. And let me just kind of cut to the chase. What you actually get when you calculate this is something which is not equal to the parameter we were trying to estimate. So again, these details are in the book. It's just some algebra, but I don't think the best use of our time here. The point that I want to make is, how do we check to see whether something is unbiased or biased? We check whether the expected value equals the value of the parameter. So just because some maximum likelihood estimators are biased, some are unbiased. So it's not that maximum likelihood estimators are always biased or unbiased. It really depends. In this case, the estimator for mu was unbiased. The estimator for sigma was biased. However, right, as n goes to infinity, n plus 1 over n approaches 1, right? So as n gets large, our estimator becomes less and less biased. And that's a really good thing to have. Sometimes it's not that important that we have a little bit of bias, but what would be really bad is that as samples get larger, if the bias is getting larger, that's a really bad thing. Here, what we can see is the larger and larger our samples become, the better and the less biased this estimator becomes. So we would say that this is if you ever want to like start a punk band asymptotically unbiased, that would be a great name for a punk band, I think. So that means as n goes to infinity, this thing is unbiased. What you can see is that if I took that original estimator and I divided it by, if if I multiplied it by this, I should say, this would fix the biasedness, right? If I redefine a new estimator, because I could just pull that constant out, and then we just showed that the expected value of our estimator at first was not exactly sigma squared. But if I tweak this just a little bit, then suddenly we can get an unbiased estimator. And let me just say that estimator sigma hat was originally defined as this. So we get a cancellation of those ends. So we can see that this sigma squared estimator that we tweaked a little bit is actually an unbiased estimator. So when we are doing this, that's why we have this little correction that we can make in the standard deviation for the sample. I'm sorry, this is a minus here. I'm realizing these were all minuses. So sorry, when we calculate this expected value, we get n minus 1 over n. And again, the details of that are in the book. So that's why multiplying by this factor n over n minus 1 kind of takes the bias out. And what we get as a result is this formula that we use for the standard deviation for a sample. That's why I realized I was wrong. This should be n minus 1 for the standard deviation of a sample. So it's just nice to see, you might have thought to yourself, why is the formula for the standard deviation of a sample different than what we would do for the population? And that's because that is not a perfectly unbiased estimator. Unless we divide it by n minus 1, then it becomes unbiased. So one property that we've already talked about in terms of measuring how good is your estimator would be, is it unbiased? But I'll just say the goal is not always to have it unbiased. There are other properties that might also be worth exploring. And one of them is, okay, if it's not unbiased, at least as n goes to infinity, is it becoming more and more unbiased? Okay, another property of estimators is what's called the efficiency of an estimator. And so just to take a look at an example, let's just say, we take a sample of 3 observations from some population. And I want to come up, based on these 3 values, I want to come up with an estimate for the population mean. So here's kind of the standard estimate that we do for a mean, right? We just calculate the sample mean. Here's a second one that we've seen before, which is the weighted mean. And so we could say, okay, let's put more weight on X3 than we do on X1. So maybe some things in our sample are more representative than others, okay? And a case might be, if you think about like the homework problem that you had a couple of weeks ago, where you were trying to calculate the mean commute time of people into a city center, and it wasn't that the same number of people take public transportation and drive and ride their bikes in, but we had different percentages of the population commuted in different ways. So when we wanted to calculate the mean commute time, we might want to weigh some of those observations differently. And so the first thing that we can ask is, are these estimators unbiased? And so we can say, okay, does the expected value of y give me the population mean? And so for example, y so if I take the expected value of y, we could just use the linearity of it, right? And since each of these observations, X1, X2, and X3, all come from the same population, they all have the same mean. Okay, so that's how we could check that estimator, that weighted mean, is also an unbiased estimator. So what the efficiency, measures is the variance of these estimators, right? So one thing is, it's great that we want, on average, our estimator to equal the actual population parameter, but it's not always going to equal. So when we say it's unbiased, that means on average, it's going to equal the parameter it's trying to estimate, but it's going to vary a little bit. So here we've got two estimators, which are both unbiased, this one and this one. So then we might next want to consider which of these estimators has more variability. And it is going to be desirable in an estimator, like we want it to not be very biased, and we also don't want it to vary all that much from sample to sample. So that's what the efficiency is measuring. So I could calculate the variance of this estimator by taking the variance of X1 plus X2 plus X3 all divided by 3. And so just recall that with variance, when we pull out constants, right, they get squared. So I've got the 1/3 comes out, it gets squared, and then inside, then we can break up the sums because we're assuming that these guys are independent. So for estimator number 1, which is like the pretty standard sample mean, we can calculate its variance is the variance of the population divided by 3. And if we do the same calculation for this one, now we pull out each of these constants and we get 1/36 and 1/9 and 1/4, and we get a slightly different variance. And since 1/3 is less than 7/18, this one over here has less variance. Sorry, got a slight delay here. Less variance. So we would say that it is more efficient. So not that surprising. Like, we can start by thinking about the expected value of an estimator and we hope that the expected value is equal to the actual value. So we hope that it's unbiased. But we might not even care. Even if there is a little bit of unbiased, sometimes it might be more preferable to look at which is more efficient. In other words, look at the variance of the estimator. And that's another nice desirable thing, is we want that variance to be small. The smaller it is, the better. So that's this notion of efficiency. So we kind of have two things. Okay, so if we can show that the expected value is equal to the population parameter, then we say it's unbiased in its grade. Sometimes things are a little bit of bias is fine. So that's another property that we might be after. So you might hear some people talk about estimators being efficient, and that just means they have a small variance. Okay, so that's kind of a new thing there. We haven't talked about the efficiency of estimators. Lastly, this is certainly not gonna, you guys aren't gonna be tested on the mean square error. This is a tricky thing, but I think it's really nice because this measurement takes into account both the efficiency and the bias. So we've talked about, okay, what is great? We want them to be unbiased. Okay, sometimes it's not so bad if they're a little bit biased, but they have a small variance. So the mean square error is a measurement of how good is your estimator that takes into account both how much is it going to vary and how much bias is there. So this is another property of estimators, again, which really takes into account the first two estimators. Okay, so maybe I'll just stop here and I'll just say if you're curious about this part you can consider optional, but I'll kind of put up a little video that kind of walks through this example as well if you're kind of curious about how mean square estimates work. But yeah, you'll see kind of another estimator for the population proportion is the consideration here. So let me just say kind of the motivation behind this example is if we want to approximate the population proportion P, a very obvious one is to take the sample proportion, and we've done that. And we've been able to show that the expected value if X is binomial, then the expected value of X is n times P. So that we just proved that that is an unbiased estimator, right? Because when I take the expected value of it, I get P. If we think about this other estimator for the sample proportion, maybe it's worth just saying a little bit about this because we'll see some similar things come up for different ways of finding confidence intervals. But what you can think about here is we've added 2 attempts to our sample. So down here, right, that's what the +2 is. And we're going to assume that one of them is a success. That's the one up here. So really, we're going to take the number of successes we observed, which is X, add one more success to it. We're going to take a look at the number of repeated trials that we did, and we're going to add 2 additional trials. So basically, we're saying, let's take our sample that we observed. Let's pretend that we were to do 2 more trials and one of them were to be a success. And this gives us another estimate for the population proportion. And if we want to check this expected value, right, then we would get, we could pull out the 1 over n plus 2 and use our properties of expected value. Expected value of X, right, is, since this is binomial, would be n times p. The expected value of 1, what do we expect 1 to equal? We expect 1 to be 1. And so we see here that we actually do not get an unbiased estimator. We are not getting actually P back. So this one is a biased estimator. Okay, any questions? But I'll just, sorry,
thank you for giving the explanation on all the theoretical stuff behind the formulas.
Yeah, I have some videos. So like last year at this time, I was also teaching stat theory. We were live half the semester, and then we were abruptly kicked online. And so we're past the point where that class went online. So I can just tell you that, like, in spring of 2020, last year, when we went remote, I was not doing Zoom stuff like we are right now. I was making like pre-recorded videos. So you might find going to like the playlist for Math 3382 for spring 2020, those videos might be really useful to you as well, because those are just me talking. There's no back and forth with students, which is maybe good or maybe bad, but at least like they're a bit more short and direct and to the point, because I'm not having a discussion, I'm more just presenting this stuff. But I'll put up some of these videos about the theory as optional in case you're curious about them. For whatever reason, not many people in the world watch my YouTube videos other than you. But like some reason I made some video, I don't remember which one. One of these videos that I made about the theory behind this stuff, actually other people have appreciated. So maybe you'll like them. I get some random comments from people sometimes like, hey, I've never understood efficiency. The main point in chapter 6 is really looking at section 6.1 and 6.2. 6.1 is going through finding maximum likelihood estimators. 6.2 is going through and finding method of moments estimators. And then the stuff in 6.3 is a little bit more optional. And that's really getting into how do we figure out which estimator is better than the other. And that's a really complicated question because there are different metrics for measuring that. Is all I want, is really the main point I want to say about that. Okay, so definitely get going on the first 3 questions on the homework. The question 3 is very similar to the uniform distribution one that we worked on together. And on Wednesday, we'll start chapter 7, which is working with confidence intervals from a non-bootstrapping, not from a simulation point of view, but from a more classical theoretical point of view. So we'll take a look at other ways of constructing confidence intervals on Wednesday. So the idea of a confidence interval at least is familiar to us, and we'll just think about some new methods for calculating them. Yeah, so otherwise, I also want to say I did go through and grade your exams, and I posted my comments, you know, in an attached PDF where I marked them up. So you can see your grade on exam 2 posted. I didn't have a chance to write individual comments out to people, but I'll just say, I think like, I don't know, overall the average was, you know, it was somewhere between a 75 and an 80, maybe a little bit over, I think maybe about 77%. But I would say I would be, if you found that your exam 2 is kind of moving in a different direction from your first exam. So if you did a little bit worse on exam 2 than you did on exam 1, you know, it might just mean, you know, it was a bad time for an exam, you had a lot going on, or it might mean that there's, you know, like a more severe hole that we might need to fill in. So I would just like to encourage anyone that is, you know, not happy or concerned about how the exams might be going, to reach out and talk to me. I'm here to help you guys. And so I want to make sure that we're not leaving anybody behind at the station. So, you know, if you did great and you want to get some feedback on how to improve, I'm also happy to have those. But for students that might be concerned about how you're doing in the class, please don't be afraid to reach out and contact me. I'm here to help you, and I want you all to succeed. So if I can help at all in that process, just let me know. Otherwise, I've got office hours tomorrow. So if you want to chat about that or about your homework, I've got office hours from 1:30 to 2:30 tomorrow. Otherwise, I'll see you guys on Wednesday.